So now we have an example of this line integral. We have the function f and the given curve we want to evaluate it. So we hear that at t0, x will be equal to 0, given like this, and at t equals 1, t will be equal to 1. And in order to obtain a primary representation of c, it is easy to see that x with respect of time will be equal to t. Seen here, sorry, this is x. And it's easy to then get that the primary representation of c will be equal to t, 4t squared. As x is equal to t and the equation is given as this, it's easy to obtain this new primary representation of the curve. Now we know that the line integral is defined as this, but another representation of the line integral is as follows: hb of f divided at third are dependent on time, and the product of that with the derivative of the primary representation on time times the derivative. Okay, now we will need to obtain the derivative of the primary representation, which will be equal to this 8t, and f evaluated at rt. It's easy to see that it will be equal to 16t to the fourth minus t squared, because we're substituting this y with this y over here and this x with this x over here, and we're getting this. Okay, now we know that the initial value will be equal to the time 0, equal to 0, and the last value will be equal to the final time, which is equal to 1, and hence the integral will be as this: 16t4 minus t squared, the product of that with 1, 8t dt. Okay, now we just make the dot product, which will be equal to this minus 8t cubic dt. And now it's just a matter of solving this integral. It's really easy to see, and we can just make this kind of evaluation. 0 to 1 of t cubic dt, which will be equal to 16t to the 5th over 5 evaluated from 0 to 1 minus 8t to the 4th over 4 evaluated from 0 to 1. Okay, now we will be having 16 of 1 times 5 minus 16 of 0 times 5 minus 8/4 will be 2, 1/4 minus 0 to the 4th, and this will be equal hence to 16/5 minus 2, and where will we have 16 minus 10 over 5 equals 6/5, and that will be then the result of the given line integral. And that's how we can solve line integral. It's really easy. Well, another kind of problem is when you have a given vector function and the parametric representation of the curve. This can also be evaluated, as we were talking about. We have this kind of evaluation, and this is a product. However, we are said that what we are willing to obtain from this evaluation is just a vector, a line integral that gives us a vector, and that will be requiring us to make this kind of evaluation as depending on r and the derivative of time, and this will give us a vector. Okay, so then we will needing to obtain the integral of the curve of the given function f evaluated at r. And it's easy to see that it will be just leading us to do something like this. 3t squared comma 3 cosine of t squared dt. Okay, so let's say this is f1, this is f2, and this is f3, and hence you just need to do these kind of things. Plus the integral on the curve of f2 dt plus the integral of c of d3 dt, and this will give us I vector, just as easy as that. We'll not be solving this, it's just to understand the concept of this kind of integrals, and well, we will just we can just see this other kind of line integrals where we have a function f equal to 3x plus y plus 5z evaluated at this given curve. And we know that this kind of integrals can also be evaluated at this. And this, instead of a vector, will give us a scalar. Okay, so it's easy to understand that this kind of integrals can be evaluated at this, where we have that x is equal to t plus y, where y is equal to hyperbolic cosine of t plus 5 times the hyperbolic sine of t dt. And we can see that this will easily give us a scalar. It's just a matter of solving this integral over here, so it's just easy to evaluate this kind of integrals, and that's how we can solve some example of line integrals.